Hello everybody, we're going to be talking about magnetic torque on current loops. So let's just get into it. Right here I have a diagram of a magnetic loop in brown. We have it connected to this battery down here, this side being positive, this side being negative. And when we connect it, we're going to have a current running through it going in the direction of these black arrows around the loop. We have two magnets, one over here and here, these blue boxes, which makes a magnetic field going in this direction with the blue arrow. So when we have a metal loop with a current running through it, influenced by a magnetic field, we get what's called a Lorentz force. This Lorentz force is going to rotate our loop. It's going to turn it. Now, how do we find out which direction? Well, if we know the direction of this current in the loop, we know the direction of our magnetic field, we can use what's called a right-hand rule to figure out which way our Lorentz force will be. So we take our right hand here, we're going to put our thumb in the direction of the current on this right side. It's going this way. We're going to stick our fingers out in the direction of the magnetic field, and whichever way our palm, so this my palm, whichever way that's facing is where the Lorentz force will go. So that's going to go into the whiteboard. On the right side, if we do it on the left, going to be a little hard. Going to pretty much turn my hand upside down because we have, here we go, fingers pointing towards the magnetic field, thumb pointing down because that's where our current is going, and our palms facing up. So our Lorentz force will be coming up. And so that's what these two symbols mean. This circle with the X through it means that the force is going into the page. This circle with the dot in the middle means it's coming up towards us. So if we were to construct this as is, we would experience the Lorentz force in here, which would cause this to turn like so. Now we haven't built a motor yet because we run into a problem. Since these wires connecting our magnetic loop to our battery are fixed on these two spots, this current will rotate with the loop, meaning that once it's rotated halfway, that these arrows will pretty much change direction. Won't be going this way anymore, will be going this way, the opposite direction. So if it's going the opposite direction, we pretty much have, using our right hand rule, the current going down on the right side with our thumb, our fingers pointed this way with the magnetic force. So the right side will have a Lorentz force going up, and the left side will have a Lorentz force going down using our right hand rule, which means that these two will be opposite. So once it rotates halfway, it's now experiencing opposite forces. It will stop and rotate back to where we began. And it'll continue to do this indefinitely until our battery power supply is exhausted. So it'll just continue to oscillate, and that's where we run into a problem. In order to fix this problem, I made my own magnetic loop, and I put a wooden skewer in the middle of it. I have my two exposed copper ends next to where my hand is. The idea is that when I put two other copper wires on either side of this skewer to touch these other two wires in the loop, that a current will be generated, causing the Lorentz force to turn this loop to this point where the contact with the battery will be broken because of the wood on the skewer, until it's here where the contact will be made again, except I'll be keeping the current going away to keep my loop spinning in the same direction instead of oscillating back and forth. So we're going to try it. Right here I have my little setup, and we're going to put a current through this loop. I have two magnets. They're not very powerful magnets, but two magnets that I found taped to cups. And I use straws to hold the metal skewer. I just punched holes through them. And the wooden skewer just sits right here, able to rotate. And so I want to position it like so. Before I put current through it, I'm going to position the camera so you guys can see how it looks. There we go. Let's focus it. Okay, so here I have my battery. It's just a AA that I duct taped these two copper wires to. Now we're going to touch these two copper wire ends on either side of the wooden skewer and see what happens. Oh, it stopped for some reason. Let's try again. There we go. Alright, so here we have electric motor. So we solved the problem of oscillation. And so how this changes into motors that we know of today is that we're generating kinetic energy in the skewer through this loop rotating. So we could attach gears in order to transfer this kinetic energy into doing something useful. That could be rotating a car tire, that could be creating suck in a vacuum, whatever you can think of. This is pretty much the basic idea of an electric motor. It can be designed in different ways for different effects. Alright, so now we're going to go over what would cause the torque to increase on our current loop. So we have an equation up here. It is torque is equal to NIAB sine theta. And this is what each one of those means. So my torque will increase when N, the number of loops, increase. So for my current loop, I used about 11 loops, and the final 12th one is just wrapped around, holding it all together. So that's what I used to get it to go in the demonstration. I is the current strength, so when that increases, so will my torque. So I obviously used a AA battery, but if we were to increase the power source, then that we would see we'd see it spin faster. A is the area in the middle of the loop, right here. So when you construct your loop, you want it to be in the shape where it'll give you the most area. Mine is a little wonky because of the rubber coating around it. It was kind of hard to shape. So if you guys ever want to do this, I'd suggest getting just enamel covered copper wire instead of this rubber covered, so you could wrap it around easier and shape it the way you want it to. But it worked. B is the magnetic field strength, so as that goes up, so will my torque. I just used those two magnets from Home Depot that I found. They're not very strong at all, but they're able to produce enough of the magnetic field to get going. So if I were to use something stronger like an electromagnet, then we would have saw it spin faster. And sine theta is the last thing I want to talk about. So back to this demonstration. So we had the magnetic loop facing this way when we started it. And this is the best way to start it because I get the maximum amount of force when my sine angle is this. So when it's parallel to the magnets, our sine is either 0 or 90, which sine of 0 and sine of 90 is equal to 0, makes our whole equation 0. So we get no Lorentz or no torque force when it's facing like this. We only get it when it's tilted to the side, and we get the maximum force when it is perpendicular to these magnets. So that is everything that influences the torque force that acts on our current loop. So that is magnetic torque and current loops, and a little bit of how electric motor works. Hope you guys learned something. Thank you for watching.